we started talking about path loss models. The purpose is to get you guys familiar with different path loss models, but we won't really discuss a particular path loss model in detail, or uh, we won't spend too much time on a particular model, path loss model. It's because there are many different path loss models, and new path loss models are also developed uh, pretty often. So it doesn't make a lot of sense that we learn a few models very well. And also models are very simple to learn. Okay. Uh, so so it rather makes sense that you just get an idea what they are and how you can use them. Its use is also very simple. Okay, so then you can actually use a new model. Okay, when you encounter a new model which is which is newly developed, you will also be able to use it. Uh, so we already mentioned that the actual environment has too much complexity. There are so many uncertain things. It's not really possible for someone to accurately estimate how much the loss there would be. Well, of course, in the case of pure LOS communication, like freeze, we when you derive the equation freeze space communication, then we had good estimation for this that kind of cases where you have real LOS communication, very confined. Okay, there are no other ways you get signals to the receiver. Then it's pretty easy to determine how much loss or attenuation of the signal there would be on the way. But in other cases, it's not that easy, especially as you make it more and more non-LOS. Okay, so this particular discussion, although doesn't always specify cellular environment, but mostly they address cellular type of environment where it's completely non-LOS and so many things there. Through wide radiation pattern or radiation beam, the users are accessed from the base station. And in the uplink, we already mentioned that the radiation pattern, okay, is omnidirectional, so even wider. So the signal gets to the other end through many different paths, and that makes things very complicated. It's never possible to estimate accurately, or even something that will be close to the accurate values. Okay. So the estimations are always crude, but a lot of attempts are made so that the estimations are just uh, good as much as possible. And these models, their purpose is just to show you how much loss of the signal you have on the way. So you call them path loss model. Also, you can write down in a way that gives you directly receipt power. Okay, so then basically from PTGTGR, you are subtracting path loss. Okay, or you may put them this way. Okay, just multiply P with G. So either you show the receipt power or you show the PL, okay, in the equation, in the representation of a particular path loss model. Now we were discussing that there are three ways you can develop a model. The first one is deterministic, shown as the last one, where you develop the model, okay, completely based on the different theories. So direct ray, reflections, diffractions, and all that. But more popularly, people use empirical models, which are based on experiments. You test the loss of the signal at different points, at different distances from the transmitter. And then from this measurement results, you just estimate with distance how the losses are changing. Okay, so just feed them into some curve or equation that can represent the path losses, and then you use it for any new case. But of course, you have to do it for a particular type of environment. It can be city area, it can be suburb area, it can be rural area. So you got to mention what type of environment it was. The middle one, semi-deterministic model, is something in between. I mean, which uses both concepts and it tries to combine the two concepts. Because in some cases, the theoretical development may help you a lot. Okay, uh, but it may not be enough accurate. So if you add some experimental information, I mean, if you tune your theoretical development according to some experiment results, or tune or modify, then the model you develop, okay, how the path losses on the way is changing with the distance and frequency and with this type of parameters. So this may better represent a particular scenario. Okay, well, this sorry, I have some slides this one here. So measurement data, and so it implicitly accounts for both known and unknown factors, empirical models, and some examples of empirical models. Okay, so I'll come back here, but the other type, semi-deterministic model, okay, which combines both concepts. Okay, now it basically depends on how the environment is. If the environment is enough predictable, okay, the uncertain things or random cluttering up is less, then the theoretical models may help you. If it has two uncertain objects, two random clutters, and I mean very much unpredictable, then empirical models will be helpful. If you have the scene condition somewhere in between, then the semi-deterministic models may help you. Well, the first one, which became very popular as Okumura model. I mean, Okumura tested a lot in Tokyo. You see, it dates back to 1968. So long ago, this actual activities started, and based on extensive tests, he developed a model. Although we are saying it's model, okay, it sound, I mean, it's high sounding words, but
So wasn't there only three models, sir? Where did this come
I
from?
mean, these are just classes. These are just classes. Okay, 3 classes of models. In each class, there are plenty of models. Okay,
Oh, yes.
plenty of models are there. So we'll just show a few examples, but new models are developed very often. Okay, I mean, as by the time you graduate, many new models will come out. So it's an ongoing process to develop models that fit in certain requirements for certain environment conditions, okay, certain frequencies or certain type of applications. So under empirical model, we'll discuss a couple of examples now. The first one is Okumura model, and this is I mean the most popular early model. For a long period, Okumura model was applied, and it was little modified by someone named Hata. Okay. So later a combination, I mean this after this modification, it was called Okumura Hata model. Okay. So first Okumura model ran for a long period, and thereafter Okumura Hata model ran for another long period. Um, we're showing the Hata model here, okay, and it is still popular. Okay, it's not used that widely now, but the different tools still have this feature of Hata model. Uh, so I mean, it is enough reliable. You see that they have different expressions for urban, suburban, and rural areas, I mean open areas. Okay. L here gives you the amount of path loss, and these 3 questions are actually the model. Okay, so the model, I mean, it's high sounding words, but it's actually nothing but an equation. Now here you see these constants A, B, R, C, all these things shown here. Okay, have some awkward expressions, but if you use I mean, if you just write down code for it, then quickly you can calculate everything. It's just for different frequencies. I mean, the values you need to put here, the carrier frequency, and HB is the height of the transmitter, HM is the height of the receiver. Okay, and also the model is valid for certain range for them. For FC can vary between 150 and 1500 megahertz. HB, or the base station height, the transmitter height, has certain range, the receiver height has certain range. The maximum distance between the transmitter and receiver is 10 kilometers. Okay. So once you put all these values, and of course the distance, R is the distance here, then you can get the path loss, how much signal you lose on the way. Okay, so for different distance, for certain setup conditions like base station height or carrier frequency and mobile height or receiver height, you have this, I mean, all these values constant, A, B, E, C, R. Then for different distance, you can find out the path loss or loss of the signal energy. But the maximum frequency was 1500 for original Hata model, and it was found insufficient. I mean, later, many new, I mean, for increased data rate, people added 800 bands in Asia, Europe, and 1700 band in North America. And also later, the bands around 2100 or around 2 gigahertz or 2.1 gigahertz. Okay, the frequencies were added. So people needed little larger range. This Hata model stops at 1500 megahertz. So a further modification of this Hata model was developed by a research body named COST. Okay, uh, so their modified equations can work up to 2 gigahertz, and this model is actually also used up to 2.1 gigahertz. Although I mean it shows 2 gigahertz, but practically it is used up to 2.1 gigahertz. I mean for frequencies up to 2100 bands. Now the equations, okay, I know you guys are very smart and very good. I mean you are not like me,
No, sir,
so
we are
so
becoming
you
dull,
are,
sir. We are
you
becoming dull,
can
sir. Every day.
uh,
Throughout this
I,
online phase, sir, we are becoming dull, sir. This is a fake news, sir, that we are smart, sir. We are not smart, sir. No,
well,
no, no.
I know you are
No, 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 sir. You know
well,
wrong, sir. I tell you, sir. This is not right, sir.
that shows your, I mean, anyway, there's like feeble-mindedness, okay,
And yes, sir, because we
but
have turned
in
into
fact
like
you are
this, sir.
smart. You can memorize all these equations very easily. Uh, I know. Okay,
No, sir.
but I must consider someone in the class who is not that smart, who is like me. Okay, so I need to consider uh, this. I mean, this kind of students, although they are very few. Okay, so for them, uh, I mean, they can actually use all these things. I mean, the exam will be open book, so they can actually use the books. Okay, but for the rest of the guys, I know, I mean, you can memorize, so you don't have to look at the books, okay, or the slides, right?
Yeah.
Okay. Well, uh, now it's another example. Okay, so these are the purpose here is not to actually, not like you learn here and then you start using. No, you just get familiar with the different models, so you come to know there are many other models. Okay, I'm just showing here two examples for empirical, but there are many other models. RSEC model is just another example, and you see, I mean, for PL you have an equation where for S, okay, there is a table. So did I miss anything? Oh, sorry. For S is just a shadowing effect. For gamma, there's an equation like this. HP is like the base station height, and for ABC, you have this table. So different types of terrain, there are different values. Okay, like in the case of Hata model, there are different versions for different types of environment. Similarly here, they treat the environment with different types of terrain properties. Like category A is like hilly terrain with moderate to heavy tree densities. Okay. Then category B is a hilly terrain with light tree densities. Okay, or flat terrain with moderate to heavy tree densities. And category C is mostly flat terrain with light tree density. Okay, so for different types of terrain properties, uh, RSEC model shows pretty good results. Now there are many different models, and each model is popular for certain types of environment, for certain frequencies. Okay, uh, so you just can pick I mean from many choices you can just for the best one for your application. Now for semi-deterministic model, we are showing an example here. Again, it is developed by the same body, cost, okay, and it is called cost 231 Wolfish Ikegami. I mean, initially it was proposed by those people, Wolfish Ikegami. Now this model is mostly used for an environment where you have, I mean, narrow alleys between houses, like the sorry,
Like Old Town.
like the old town, yeah, okay. Especially, I mean, old town in old town of Dhaka, okay. Not every old town looks like that. There mean, I mean, different many cities have their old types. I mean, the old parts of the cities uh, have uh, I mean just houses which are sparsely located, so they don't have narrow alleys and the houses are low height, okay.
As
But
talking about Old Town of
in this
Dhaka.
case, yeah, but yeah, I know you are correct. So it is like I mean in many countries also, London also has, like, you know, it has old town like our uh, Dhaka old town. So of course there, so you can see that here you need to mention the height of the buildings, okay, width of the roads, and then building separation, okay, and road orientation with respect to the direct radio path, okay, how it is incident, like here this way, this figure. uh, so anyway, these things are taken into account for those kind of areas. Different tests were done, and also there was some theoretical development, okay. So these both um, analysis were combined and this particular model was developed. And again, this model is just an expression, okay. uh, for non-LOS, the expression is pretty complex, okay. But again, you just come to know the different values for different parameters, put them, and then you can find out the loss, okay. So sometimes the expressions look complex, but it's not a big deal, okay. You just need to have the values of different parameters, put them, and then it calculate. So the path loss models are always simple to handle, okay, but may very difficult to develop, okay. Now for deterministic model, that free space equation may be our first example. That was, you know, completely developed on our theoretical understanding, and it is also very popular. I mean, it is found valid for many applications like the satellite communication, okay. So we also probably discussed this log distance path loss model before. If not, then let me share it now. That we had an understanding. We had some derivation. Yeah, I remember that we considered a path loss at a reference distance, and then compared to that, the loss was estimated for any other distance. So then you use a ratio. Now, when we discussed the free space equation, the path loss increased uh, at the rate of d square, I mean it was proportional, the receipt power was inversely proportional to d square. So the path loss was linearly proportional to d square. If we take all these things in dB, path loss in dB, then what we would get? We would get 20 log d by d naught. Okay, I mean, if we just have a ratio, I mean, take the ratio with d naught, then is d square. So in dB, there will be 20 log d by d naught. The value of path loss exponent or n is then 2.
So this is the
This is the
deterministic model type.
this is the determinism. I mean, this is actually this is basically the I mean we if we put the value of n equals to 2, then this particular model is nothing but what we have for free space equation. Exactly the same model. Probably you remember that we had for free space equation, the path loss was shown this way. I mean, when we wrote down in dB, okay, in the denominator what we had, but free space equation, space equation is like ptgt divided by the square of this term 4 pi d by lambda, right? In the denominator you had 4 pi d by lambda square. So when you take them in dB, ptgt you take in dB, and then you need to subtract the path loss. But because of square, okay, you can actually use 20 log, then you actually have removed the square already. So that part you subtract from ptgtgr. That is your path loss. The path loss is subtracted. Okay, so the path loss itself is something you take positive. It is plus 20 log 4 pi d by lambda. That's a positive value. But this path loss you need to subtract from ptgtgr to get PR. Okay. So it's 20 log 4 pi d by lambda. Now, if I take a reference distance d naught, then compared to that, how the path loss would increase? D square by d, I mean, the ratio, I mean, it is inversely proportional to d. Okay. So, I mean, compared to that, you have a d square, or I mean, if you know it for d naught, if you know the path loss for d naught, then you need to multiply it by d square by d by d naught square, right? So as you take logarithm on that, then the path loss for d naught, okay, and then plus 20 log d by d naught. Okay, you multiply PL d naught by d square by d naught square, or d by d naught whole square. So when you take in dB, then you just get PL d naught plus PL d naught in dB plus 20 log d by d naught. Now, using something called path loss exponent, we are showing it as 10 times 2 using n equals to 2. Then, I mean, this thing we actually explained when we discussed free space equation, and thereafter we also touched upon this fact for two-ray model. Then we made a comment
Sir,
that
it's like
in the case of
we have to find the value of d naught in normal logarithm, right, sir? It is also in dB. That
it's in
PLD
dB,
naught.
right,
Everything here
PLD.
is in dB, right, sir?
Yeah, right, you're right.
Okay, sir. Okay.
Okay, now for two-ray model, we found similar variation, okay, with distance, but there we had a value of 4 for our path loss exponent. Okay, I mean, if we used there 10 times 4, then I mean, the relationship matches the condition for two-ray model. So we argued then for a mm, particular environment, for any environment in general, we can actually use the same form using proper value of n. So that's why n is called path loss exponent, for which you can just set the proper value for different types of environment. And how you get the proper value? You do experiments. Okay, I mean that may be the way, but the basic formula is developed using some theories. Like two-ray model was also a theoretical development. Okay, so it is actually deterministic model. Both free space equation and two-ray model are deterministic models. Okay. Now, the value of n has a range range 2 to 6, and within this range, it can specify most of the environments. Okay. Like the values are shown for different environments here in this table. Now, this is called log distance model. A little modification to that is log normal shadowing, where you add a zero mean Gaussian distributed random variable. Well, why you do that? Uh, to uh, incorporate the fact that the actual value is probabilistic, or it depends on many different things. So you may not have a fixed estimated value. Rather, you may use a range, and you may show it within the range how it is varying with different probabilities. Okay. If you want to do that, then some probabilistic, I mean, you can use some probabilistic or stochastic equation. Now, the one very common is, Gaussian, which gives you a natural variation. If you use the value for log distance model as the average, okay, and around the average, you consider a variation. Like here, the mean value, okay, the center value, mu, is what we get from our log distance model. Okay. Then we declare that the actual path loss model can have any value within this range. It can be, say, mu plus something, mu minus something. Okay. Say it can be mu plus sigma, it can be mu minus sigma, but you have different probabilities to get this sort of path loss values. You have the maximum probability that you get this value that you get using this log distance model. Okay, but in this case, with this probabilistic uh, presentation, you assume that you cannot actually specify this value for sure. You cannot specify that this will be the path loss for sure. Rather, you say that there is a good percentage, the maximum possibility that you get that value. And that probability value actually you can find from here. Now, a little higher or lower value will have some different probabilities. The probabilities are shown in the vertical axis. So you have different probabilities, and as you deviate more and more from that early estimation, okay, original estimation, what you get using log distance model. So as you deviate more and more, you have less and less probabilities. the the uh, the further you are from that mean value, the lower is the probability. And this way you can also mention that within this range, say the uh, uh, mu minus sigma through mu plus sigma. Within this range of path loss, you have a chance to get value of 68%. Okay, so there is like 68% chance that you'll get a path loss value within this range. So instead of giving a particular fixed value for path loss, you just provide a range. Okay, so the engineers may work with some range of values because they know that the path loss in reality will not have a fixed value. Right? But the probability is 68% that it will be within this range. And if you go to a wider range from mu minus 2 sigma through mu plus 2 sigma, then within this larger range, to get a value of path loss, there is 95% chance. So you are almost sure that the path loss value will be within this range. And how you're getting this percentage is from the distribution. Okay, if you calculate the area under this part, here sigma is the standard deviation of this profile, and I mean you are not adding anything here. I mean you are using zero mean. Okay, probably you know how you can calculate this the area if you have this value. Okay, if you have this standard deviation, then how you can calculate? You can use Q function to calculate the area, or you can use say error function or complementary error function. The MATLAB has ERF or ERFC. Okay, this error function or complementary error function. So with any of them, you can actually calculate the area under any area over any range. Okay. Uh, Questions?
No questions.
Okay. So the Pathos model, when you show this way, it is called log normal shadowing because you're using normal distribution or Gaussian distribution. Then we'll give some example of indoor propagation model. Okay. Of course, the propagation is a lot different inside the buildings. The path losses are a lot different. You have too many obstacles on the way. The signal dies out at a shorter distance. Uh, you, mm, I mean, we are just showing here two indoor propagation models, ITUR and Erickson's model. The example of ITUR model has this equation, very similar with what we had for log distance model. You see, this 10 log new log d, and ALF gives you the floor penetration loss depending on how many floors you have on the way. Okay. Within the same floor, you can have pretty good coverage. The losses will not be too much, but between floors, there can be too much attenuation. The loss will be high because of the thick concrete layer in the roof. Okay. So this LF can be can add a actually good value to the path loss, and as you increase the number of layers, the path loss will increase drastically. Okay. Uh, Again, there are different propagation models, but we are not discussing all of them. We are just discussing this one particular model as an example. And uh, 10 new takes on these values in these ranges. The value of LF, penetration loss, floor penetration loss, has this value. Okay. Okay. Now, last of all, we'll discuss what has been done for very high frequencies. Well, mostly people were using frequencies below 6 gigahertz. It's called sub 6 gigahertz. Okay, when you
So one
use,
small question, sir.
yeah,
Sir, this ITU art indoor path loss, sir. This was, sir, under which model? Sir,
I
was
mean
it under?
it is under indoor model. Okay,
Is it
so
like semi-deterministic model
it
or
is. I'm not sure, but looks like semi-deterministic.
Okay, sir. So
Okay.
that freeze model, the long distance path model, that was also semi-deterministic or just
No, no,
deterministic?
no. They were deterministic.
Okay, sir. Okay,
They
sir.
were deterministic. Okay. The last category we had was deterministic. We started deterministic from here, like free space equation. You see it at the bottom. The examples for deterministic models are given as free space equation, two-day model, log distance model, and log normal shadowing model.
Okay, sir. Okay.
Interpropagation model, I mean, probably you have just become familiar, but we're not discussing in detail. Now, the frequencies mostly used were below 6 gigahertz for non-LOS cases. Okay, but 5G has added the use of high frequency use. When you use below 6 gigahertz, it is called sub 6 gigahertz. Okay, so this term is very commonly used, so I have written it in the chat box. Sub 6 gigahertz was the previous experience for people, but just I mean, very recently people have started working for frequencies. I mean, well, in the research lab, of course, there are activities up to 300 gigahertz. Okay, but commercially, now people are using up to 100 gigahertz, and not for 5G. For 5G, around 28 gigahertz, but for some other applications, there have been good growth in the use of high frequencies. Now, people need with this change of trend, people now need the models for high frequencies, but that requires a lot of tests, and these new tests have been done for high frequencies, and people have already come up with a few propagation models or pathless models for high frequencies. Okay, these three are the most popular models for high frequencies. These are called close-in CI, close-in free CIF, and alpha beta gamma ABG path model. Okay, but I'm not discussing the details of these models. Again, they are just some equations. So if you can find out all the parameter values for the equations, you can actually get the ABG model value. Okay, so that completes our discussion on pathless models. Questions?
No questions, sir.
Okay, now we'll talk about noise. most students love noise. I mean, they love to make noise in the class. Okay.
Days are gone, sir.
Oh, those days are gone. Oh,
Yes,
oh, yeah, yeah, right. I mean,
yes.
right.
Very the
Is-
new pathetic normal, sir.
Yeah, yeah, yeah. I just remember our days. Okay.
So
Sorry.
we remember our first year in university also, sir.
Uh,
We cherish it very much, sir.
no, I mean,
Yes, sir.
oh, so give me a second. I mean, that Zoom
Sir.
is.
So it will be very funny if we graduate online, sir. Very different from what we have thought when we got into university.
Um, I mean, now it looks like things will persist. I mean, you'll be graduating online, you'll be interviewed online, you'll be working online. Um everything will be online. Even I don't know, uh, you'll probably get married online. Okay,
Oh my God.
Yes, everything.
Yes, sir.
Things are just anyway. The whole career. Okay. Okay. Now, noise in the case of wireless receiver is very important because I mean not always, but in some applications, as we'll see shortly. Uh, Only because the wireless receivers work with very low power. Okay, every circuit has some noise. Uh, Everything has some noise generation. Okay, every material or every object has some noise generation. There are different reasons, but most importantly, the thermal noise is because you have some thermal vibrations, okay, inside the material. The atomic vibrations generate some signal around the object. Okay? So you can't avoid it. Um, I mean, these vibrations can only stop at 0 degree Kelvin. Okay. But the vibration increase with temperature. So this noise is called thermal noise. Okay. Uh, so that is the prime factor you use to like, estimate how much the noise is. Okay. So the room temperature is used to estimate the thermal noise. And there can be some other types of noise also in the environment. So in a circuit, okay, whether it is your receiver circuit or any other type of circuit, you will get some noise around any across any part of the circuitry. Say you have a big circuit, but if you hold the oscilloscope across any component in the circuit or across any part of the circuit, you'll see some small fluctuations on the oscilloscope. Okay. So some um, generation of voltage will be there, and this is small fluctuation generated from the mostly from thermal noise. Okay, uh, is normally uh, not considerable in most circuits, because in the circuit you work with pretty high voltage level or pretty high power level. So the small fluctuations from thermal noise uh, you can ignore. Your results will not be significantly affected. The power level from thermal noise very small, so you can ignore for ordinary computations. But in wireless receiver circuit, you work with very low power. I mean, the power you work with, the desired power, is very low. In the ear, the power level is already low. You catch from there as much as you can. The antenna cannot capture the whole power intercepted onto it. Okay, so eventually at the circuit, you get very, very, very low power. Now the small noise power can be significant compared to your receive power, compared to the desired power you have in the circuit. So this is why noise you need to take into account. And there are other types like short noise, flicker noise. Well, uh, short noise is something you have for active devices, okay, uh, transistors or whatever. But thermal noise you have in every types of materials. Flicker noise, well, uh, it is also in active device. Uh, I don't remember actually much about flicker noise, okay, but it's there in the active device. Plasma noise you have in the ionized gases, and we discussed ionosphere, right? That you have some ionization and creation of charges. So those are also plasma noise. Finally, quantum noise, it results from quantized nature of charge carriers and photons. And actually, when you discuss quantum mechanics, uh, the quantum noise is also a topic in this quantum mechanics. But the noise of these later types, from short noise through quantum noise, are either they don't exist everywhere, or they are very low in power. Okay, so mostly you need to consider the thermal noise. The other noise types are either absent in your particular circuit, or a part of the circuit that you're considering, or they are very low. Okay, the thermal noise itself is not high, but uh, I mean it can be significant when your desired power is low, but other noise powers may still be insignificant. Okay, how you get this thermal noise? Those types of noise you may get from the circuit you have. Okay, but there can be also noise from the external environment, like from the ground, from the sky, or even from the stars. So, wow, but that must be very low. Okay, so it depends on how sensitive your equipment is, your circuit is. For very highly sensitive equipment, I mean, this type of noise you may have to take into account. These noise levels are very, very, very low, definitely. Okay, but there are very sensitive circuitry in the space shuttles or space stations. Okay, so you may have to take this noise from stars into account for those type of circuits. Okay, these things also generate noise in the environment. Okay, and this list also includes our wireless devices. Okay, so the noise I mean, it's not here in this case, we are not talking in terms of interference. Okay, so the wireless device can generate some noise. Okay, I mean, it's not using the antenna to send the power. Okay, but I mean, the desired power that you launch through your antenna is something that you call interference. But you may have some noise produced, okay, in your circuitry, and that is launched by your antenna. Then you used to call it noise. Got it? Another device has some noise. Okay, that's not the power that it generates for launching through the transmitting antenna. So very small noise for maybe generated, but that may be launched through the antenna, and you may have to receive it. So it is then the fourth item in this list. Noise floor gives you the level of the noise that you have within the fluctuations. Okay, so you sum up all the noise level, noise uh, power you have from many different sources, and the overall noise fluctuations you can consider using some level of power. So that is called noise floor. So the noise floor determines the lowest signal strength that can be received. Well, the third line, the last line in this slide, we'll explain later. Okay. Here, I mean, the noise floor is explained. I mean, if on the oscilloscope, you may see these kind of things. When you just, I mean, you take a passive element, you take a resistor, a piece of resistor, and hold the oscilloscope across the resistor. So you have no active power in this circuit, right? Uh, but even for a passive element, you can find out this kind of noise. Now this thermal noise power, we can show this way, K using Boltzmann constant, okay, KTB. We can show the total power level we get from the thermal noise. So let me show you how you do it. So for the estimation, we will use three things: the temperature in Kelvin, okay, the Boltzmann constant, and the bandwidth. Okay, let me show you how. We have a resistive element, just a passive resistive element, and across that we are measuring the voltage. So because of thermal noise, we find these fluctuations on the oscilloscope. Now, the RMS value for this type of fluctuations is given by this expression. Okay, don't ask me how. That's a, I mean, that's like that has actually long explanation, but it's called Planck's blackbody radiation law. Okay, uh, so I mean that complexity we are skipping. Okay, so I just want to make my life easy. So this type of deep physics we'll not discuss here. The voltage that we expect from here, okay, has a RMS value this way. Okay. Now, in this expression, the different things are already specified here. Like you have Planck's constant as h, b as the Boltzmann's constants. Okay, and you have a t, and this sorry, k is the Boltzmann's constant, and b is the bandwidth system. F is the center frequency, and R is the resistance. Now, if you expand this expression on the right side, and then take the first two terms of a Taylor series. Okay, expand using Taylor series, and then take the first two terms. Then you actually get this value, HF by KT. And Sorry, I may be missing something. Okay, so the denominator e to the power hf by kt minus 1. Only this denominator we have expanded here. Okay, and the Taylor series approximation gives us hf by kt. So we need to put this denominator value hf by kt here. Okay, and if we do that, then we can cancel the hf between numerator denominator, and then we get this value for our vn. So this is called something Rayleigh-Jeans approximation. Okay, anyway, whatever it is. Now we'll consider that our signal passes through a filter and it does not allow anything except B. So it's the ideal band pass filter. And so at the right end, we have only, in the spectrum, only B part of the components. Okay. Now we'll assume that as we connect the the situation was like this. You have some voltage, okay, and you have some resistance here. Now this part you actually connect somewhere, or this resistance is connected to the rest part of the circuit. Then you have some thermal noise generation, some voltage generation, and this one you can consider like a source, which is sort of say driving the rest circuit. Okay, so how much power you are actually then sending to the rest part of the circuit. Okay, the circuit is connected to these two nodes, these terminals. The thermal noise power generated from the resistive element will be delivered to that circuit part. Okay, so you want to find out how much noise power you are actually delivering there. Okay. These power levels are very low though, but we assume that on the left side we have drawn an equivalent of that piece of resistor. We assume that the signal goes to the other end through a band pass filter, so only B is part of the spectrum goes there. We also assume that the rest of the circuit also has a resistance R. Okay, this assumption comes from the fact that we have maximum power transfer when you have the matching of impedance. Okay, so we have a power transfer equal to Vn square by 2R. Okay, the voltage Vn now is used in the circuit. So you have the total resistance 2R. Okay, so the current you have equals Vn by 2R, and that current you can square and multiply by R. Okay, so you get the power at the right end. So that is the power delivered to the rest part of the circuit.